me go ahead and record. And so again, quick reminders. If you want to join a study session, 8 a.m. on Wednesday on Zoom, we'll do that. Bring questions. And second, on your lab at the top of the OneNote, put your group member names across the top of that OneNote page for me. That'll be very helpful. All right, let's go ahead and talk about some review things for the test coming up Friday. I'm going to share a few slides with you this morning. So first off, and I've actually ordered these 1 through 6 in the order that I would prioritize them. So I'm not saying you should try to accomplish all 6 of these things. I'm just giving you 6 different options of things you could use to help you prepare. And like I said, I'm trying to prioritize them in the order that I think they will help you the most. So on Axis, there is the review sheet with solutions, and you can go through all of it. There are, all the questions will help you review the content, but these specific questions will best help you prepare for the test itself. So going through the whole review sheet would be good review of the concepts and good review of the chapter. But if you don't have time to go through the whole review sheet, these questions 5, 6, 7, 9, 10, 11, 12, and 17, those 6 questions are the ones that I think would be the most precise in terms of helping you prepare for the test. Then I've shown you before, but there are 4 different webcasts on Axis in Unit 3. And 2 of them I think are particularly helpful, especially if you're not super clear on tangent and secant lines. So one is just called Tangent Line Webcast. It's kind of in the middle of the screen towards the bottom. And one is called Solving Equations Symbolically. It's kind of on the right side of the screen towards the bottom. But those 2 webcasts I think would be particularly helpful, especially the Solving Equations Symbolically one, because we haven't done a lot of that in class. I mean, we've done that in the sense that I've shown you how a lot of the equations are derived. So we've practiced the process of substituting and replacing and moving variables around. But other than the summer assignment, that hasn't been a primary focus. So watching that webcast, I would highly recommend. Tangent lines mainly just if you're still struggling with the idea of tangents and secants. If you got that down pretty well, then that webcast probably will just be review of what you already know. But if that's a little hazy for you still, that tangent line webcast could be helpful. Then over on the right side of the unit page or the topics page for Unit 3 is a simulation called Comparing 3 Graphs. And there's actually a series of simulations. I think it's 3 parts maybe. And if you go through those simulations, it's really good if you're struggling with the graphing and understanding how position time connects to velocity time and acceleration time, which is a big part of the test this time. So just going through those simulations and practicing, seeing how they compare could be very helpful. And there's multiple simulations right in a row on the right side of that page. Underneath that, there's a velocity versus time graph area under the curve simulation. And that's also another one where if you're still struggling with how that area under the curve helps you understand displacement or helps you determine displacement, that simulation could be very valuable as well. And then at the top of that page on Axis, you can see what I recommend from the textbook, all the pages you could read, all the questions I suggest. That's also on Axis. And then there are 3 worksheets that I've used some years. This year we didn't, just for the sake of time and using other resources this year. But those 3 worksheets, they don't have keys. And so that's why I put them kind of low on the priority. And they're fairly basic, but if you just want practice at graphing, converting position time to velocity time and stuff, while there's no keys, you could practice some, and then Wednesday during the study session at 8 a.m., optional. But if you want to come to that, you could say, hey, Mr. Webb, can you help me understand this worksheet? I've been trying a couple of these. Just want to check and make sure I'm on the right track. And I can't post the answers for those because they're part of a curriculum that asks us not to post them. So, but I can tell you if you're on the right track if you want some help on that Wednesday morning. I do have to end right at 9 o'clock. You don't have to start right at 8 if you oversleep a little bit or you just want to come 8:30 to 9. It's just I'm going to have the Zoom running from 8 to 9, kind of come and go study session. Like I said, I probably won't have a lot really prepared because I'm not really sure what else to cover. I want to cover what you need help on. So come with questions and I'll just help you with your questions. So that's what I would suggest you review and kind of prioritized from 1 through 6 the order that I would suggest you take those into account. So any questions on what to prepare for, or how to prepare, I guess? All right, I mentioned this last week, but just to refresh your memory, there are 13 questions. And I think actually last week I told you there were going to be 4 FRQs, but I decided it felt a little bit too long when I was making the key. And I want to keep it to where it's like a 45-minute test. And so I trimmed off one of the FRQs and reordered a few things. So at this point now, and it is final, it won't change, it has 10 multiple choice questions and 3 FRQs. The multiple choice questions are worth 2 points each, and the FRQs are worth a total of 30. Let's see, I believe it is, I think it's 5, 9, and 16. So there's a smaller one and a medium one and a large one. And so I'm not going to really tell you much about what they are, but I am giving you some pretty strong hints by telling you which questions on this review sheet to focus on. And I'm also giving you some pretty strong hints with the next 2 slides that I show you. So, all right, questions? Are you ready to look at the next 2 slides? Okay, so part of these next 2 slides is because I do want to make sure you understand a couple concepts and things that I'm looking for. Because we're in this remote setting, there's things that you need to be able to do well that I think some of you are doing well, but some of you are still not confident with. And so just like on the last test, you are going to have to describe graphs, and you're also going to have to describe motion. And most of you are pretty good at describing the motion. I've had very few issues with that part. It's the describing a graph. A lot of students are still wanting to talk about the motion when you're describing the graph, and you're making me assume you understand things, but you're not proving to me that you understand things when you do that. And I'm not willing to assume. So you have to prove to me that you understand things. So when you are describing a graph, you should not be talking about velocity and position. You should be talking about the y-intercept and the slope or the shape of the graph. So keep it very simple and just what does it look like? What are the graph features? Okay. When it says describe motion, that's when you're going to talk about position, velocity, acceleration, and those things. So when you're describing motion, think about what are the variables on this graph, velocity and time. Okay, well, what are the units of those variables? So make sure you're thinking through those kinds of things. And then the 4 things we've talked about since unit 1. What's the direction it's moving? What's the rate it's moving? And you may not know an exact rate, but you can at least say this one's moving faster than that one or slower than that one, or they're moving at the same rate. So even if you can't give a number to it, you can at least talk about it. And then the time frame. This for the first 5 seconds, it's this, and then for the last 5 seconds, it's that, something like that. Or for maybe you don't even know a scale, but just the first half of it, the first half of the time frame, it's this, and the second half of the time frame, it's that. And then the position. You might consider initial and final. Sometimes it's not changing, but you might consider thinking about what would the initial position be? Where does it start? Where does it end? Those kinds of things. So when you're describing graphs, don't talk about velocity, position. I don't need you to tell me why the slope is what it is. I just want you to tell me what the slope is. I don't need you to tell me why the intercept is what it is. I just want you to tell me what it is. You're just trying to describe what the graph looks like visually. You're not trying to explain it. The motion part is where it's going to help me detect whether you understand it or not. Okay. So for instance, in this example, I have a graph of a car in red and a graph of a motorcycle in blue. And this you can see is a position time graph. It is not scaled, but that doesn't mean you can't refer to things such as time frame and such when you're describing the motion. So first, let me tell you how I would describe these 2 graphs. For the car, I would say it has a y-intercept of 0. In other words, it has actually, you could even say it starts at the origin. And then I would say it has a constant positive slope, or I would say it's a diagonal line going from the origin upward. And that's all you would need to say. You don't have to tell me anything about position or time, I just want you to say it starts at the origin and it's going upward positively in a constant way. Okay, diagonal line, constant. So very few words. It doesn't have to be a long paragraph. You're not explaining why it is what it is. You're just telling me what it looks like. For the motorcycle, I would say it also starts at the origin, but it doesn't have a constant slope. Its slope is always changing. So the shape of it is parabolic. Boom, you're done. Okay, nothing about position, nothing about time. Now, if the question asks you to talk about them together in any way, you could say that the graphs intersect at some point in time. Okay, but generally that would be more what I'd want you to describe in the motion versus the graph. So keep it very direct and precise. What's the intercept? What's the shape of the graph or the slope of the graph? All right. Then for motion, let me have you guys tell me. So someone unmute and tell me, how would you describe the motion of the car?
So the car starts at an initial position of 0, and then moves at a constant positive velocity for some time, and ends at a position high I guess farther away from the origin. I don't know how you'd say it, but it's like in the positive direction, farther away than where the car started.
Sounds great. You told me the direction. You told me the starting position. You told me some time frame. We don't really, there's no sense in trying to describe that too much more precisely because there's no scale or reference points. But what you said there would earn you full credit. Sounds really good. All right. So someone else, someone different, unmute and describe the motion of this motorcycle.
It's an exponential curve. It has increasing velocity over time, and its final position is it starts at the origin, and it ends away from the origin. I don't know how to describe final position.
Yeah. So you don't necessarily always have to describe specifically initial and final. I'm just saying take those into consideration if they seem like it would help you describe it. So the fact that you said it started at the origin and was moving in the positive direction, that's enough because you need to give me the initial. Okay. So the initial is really important. The final may or may not be as important, but if you're giving me the direction and some time frame, we don't really know. And then the one thing you said that you wouldn't have needed to say is you said it's an exponential curve, because what's that telling me?
Oh, I described the graph for you.
Yeah. So I wouldn't count off because you had everything else you need. But what I'm trying to get you guys to separate in your mind is when you describe graph, you're using your traditional math words, not the physics motion words. And when you're describing motion, you're just doing the opposite. So now, because he had everything he needed for motion, I wouldn't have counted it off if he said that it has an exponential curve. But he was just, for efficiency, he wasted time writing those words when they're unnecessary for that part of the question. Does that make sense? So, and what I find is a lot of you, I think you're trying to make sure you don't miss anything, which I appreciate. But you're writing sometimes so much I think you kind of get yourself confused in your own words and you start putting so much in there. You're not just sticking to the point. So stay laser focused, right? Graph. Okay. Intercept, slope. Just think about that. Okay. Don't talk about position. Don't talk about velocity. Don't talk about those things. Just what is the intercept? What is the slope or the shape of the graph? And then when you get to motion, don't worry about, I mean, you can use the word slope and stuff when you're describing motion, but you can't just stop there. So if you just said it's an exponential curve and you didn't say the velocity was increasing like he did, then you would miss a point. Because in your brain, you may know, well, exponential means the velocity is increasing, but you didn't say that. and exponential curve describes the graph, not the motion. Okay, so I want you to try to really delineate in your brain the difference between describing the shape of the graph and describing the motion of the object. And I know it's difficult. That's why I'm practicing with you today. All right, so last step. Someone tell me, someone else. So we've had Atticus and Jalen so far, so a third person now. What would the velocity time graph look like for the car? Just the graph.
It would have a y-intercept above the x-axis, and it would have a slope of 0.
Good, nailed it. That's all you have to say. Perfect. Okay, someone else, a fourth person. What would the velocity time graph for the motorcycle look like?
It would have, it would be a what's it called? A diagonal line in the positive with a constant slope.
Okay, good. What about the intercept?
It will be a 0.
Good. All right, so now to help you visualize what they've described here, nicely done. We see the car's horizontal line at some positive intercept, and we see the motorcycle's diagonal line with a constant slope, positive constant slope, starting at the origin. All right, very good. Those graphs are described. Now I want to highlight a couple things, and here's where the spoilers are coming in. So if you're listening carefully, this is going to help you a lot. Think about your geometry words and what we've done with the lab. If I'm comparing this motorcycle's motion and the car's motion, looking back at the position time graph here on the left, so I'm looking over here. Thinking about those geometry things and the things we've been drawing and thinking about in the lab, what is this red line compared to this blue line? Geometrically, what is that red line compared to the blue line?
It's a secant line.
Yes. What does that mean? What does the secant tell me?
Acceleration. Instantaneous velocity.
It can tell me the instantaneous velocity, but it's going to tell me something else. Like, it's only going to tell me the instantaneous velocity. I need a little more detail on that, but it tells me something else first.
It tells you the average velocity between those like 2 points, and if you want the instantaneous velocity, it's for like the midpoint between those 2 points.
All right, so let's think about what that's really telling us. The car and the motorcycle are two different vehicles, but because the car's line is a secant for the motorcycle, what that tells me is from the place where they both start at the origin to the place where they intersect again, where they're at the same distance from the origin, the average velocity of the car, which is constant, so the velocity of the car, is the average velocity of the motorcycle. And the velocity of the car, which is constant, is the instantaneous velocity of the motorcycle at the midpoint. So that is why these would cross on the velocity time graph at the halfway time frame. Is that making sense? Their velocities are equal at the midpoint. What's true about the velocity of the motorcycle initially?
It's 0.
It's 0 initially, and then as time passes, how about the first few seconds here? Is it less or more than the car?
Less.
Less. But at the midpoint, it's the same as the car. Right? Is that making sense? Since this is a secant, at the midpoint, the tangent of this curve would be parallel to the secant, which is the car's graph.
Wait, how is that, like, if you draw a line there? I don't understand how that's possible.
What's possible?
How they have the same velocity at their midpoint if you're like looking just at the position time graph.
So remember, the position time graph is a slope, right? And so if I drew a tangent to this curve, and it's parallel to that secant, they have the same slope. So this secant tells me two things in this scenario. The slope of this secant line, the slope of this red line tells me two things. It tells me the constant velocity of the car, and it tells me the average velocity of the motorcycle from the start to the intersection point. But if I drew a tangent that is parallel to the secant, the point where it touches the motorcycle is the time when their slopes are the same, and therefore their velocities are the same.
And
And
that's
by go ahead.
place. That's the only place that their velocities are the same.
Correct.
Okay, I see.
Because the motorcycle's velocity is constantly changing. So there's only going to be one time when it's exactly the same as the car, since the car is constant. Yeah. Is that making sense?
Yeah. Yeah. So on the position time graph where they intersect, it just means that they reach the same place position wise. Doesn't mean that they have the same velocity.
Correct. So they both started at the same time at the start line, but it looked like could be that the car was already moving. Right? I mean, we don't know for sure, but it could be the car was already moving. Either that or it just instantaneously was able to be going whatever speed that is without any speed up, right? But the motorcycle was full stop and had to speed up to reach, but it ended up in this last few seconds, what's true about the velocity of the motorcycle? If I drew a tangent up here, that would tell me the slope there, right?
Velocity would be greater than the cars.
Yeah. So if I draw a couple of tangents on here, draw a couple more. If I draw a tangent there, that's the slope of the motorcycle at roughly this point, right? And it's a much steeper slope than the car right now. If I draw a tangent down here, it's maybe there. It's kind of hard to tell. Maybe there. I don't know. That's why tangents are hard. But you can see that it would be much less slope than the car initially. Here it's the same slope. Here it's a greater slope. So the motorcycle's moving slow, faster, 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 same as the car, faster, and then it's even faster. It speeds up and it becomes faster than the car. So eventually it catches up. So if you were imagining the motorcycle and the car driving down the road, we're observing them in the time frame, the same time frame, but it looks like perhaps the car was already moving because it didn't have to speed up. So you guys have all been in a situation where you're sitting at a light and it's 2 lanes and you're sitting there stopped. The light turns green and you take off, but a car comes flying by you that never had to stop, right? It's just still going. It never had to stop. That's possibly what's going on here, right? The car just flew through because they didn't ever have to stop. You had to stop because you got caught by the light. So now, but now you're on a motorcycle, so you speed up and you eventually catch up to the car. Is it making sense? So that's how you could describe the motion. Is looks like the car was probably already moving because it was going at a constant velocity even at time 0, right? And so it was probably already moving. The motorcycle was probably stopped. Now there's a little bit of an assumption there, but beyond that, we know for sure the car maintained its velocity the whole time. The motorcycle sped up and sped up and sped up and eventually caught up to the car. And the place where they have the same velocity is exactly at the midpoint of this time frame, because that would be the midpoint of the secant, where the tangent and the secant are parallel. So lots of geometry connections, lots of graphing things to think through. Any questions for me before we move on to the lab? Oops. All right, so there's definitely some spoilers there. And hopefully that helps you think through both how to describe a graph for what we're looking for, how to describe the motion, how to keep those things separate. how, even though these are two different objects, because of the way their graphs look, one is the secant of the other. All right. I think that's it for the review. So I'll put you back in breakout rooms for the remainder of the time. So you've got 50 minutes basically. You can use as much of that 50 minutes in the breakout room as you need. I know one of the groups at least is nearly done. So if you guys only need 10, 15, 20 minutes, you know, when you're done, you can be dismissed. Or you can hang out and study together if you want. If you need the whole 50 minutes to keep working, it's not due till 11:59 tonight, but make sure you're coordinating with your group and everyone's sure, like double check each other, go through the rubric. Remember, the rubric's both in Axis and in OneNote. You can see it in either place, but go through and say, okay, do we have this? Do we have this? Do we have this? Like check it together and make sure you all agree that everything you need from the rubric is there on that OneNote page for me. Okay, any questions about that? By the way, also, I just thought of this and forgot to mention earlier, I did update the notes to include these new slides on Axis, because these slides I showed you this morning weren't there before, but they are there now. So if you go to Axis topics for Unit 3, the notes now include, I just put a newer version that includes those new slides that we just looked at today. All right, questions about the lab? Before I shoot you off into groups, you can always call me in your groups, I guess. Okay.